Wait, Professor, are you talking? We can't hear you. Wait, Professor, I can see your lips moving, but I can't hear you.
We can't hear you.
Oh, now I can hear you guys again. Am I getting through now?
Professor? Wait.
It's still not working. Your voice is too faint. Still. I don't think the professor can hear me, but can you guys hear me?
Yeah, we can hear you.
Oh, good. So it must be a problem on his end. He hasn't realized we can't hear him, has he?
Nope.
Hear me?
Okay, yeah. So I guess the question is probably about 4 minutes is how long it would take for me to notice. Sorry about that. I thought I saw my little green thing going up there. I'll have to see if I can edit that out. Okay. All right, so now that I've rehearsed, okay, this is some Python code that should be used in a manner that you can kind of link everything together. I will post it. All right. But the bottom line is this is a transfer function of a low pass Butterworth filter, right? And this can be easily scaled, right? If I just say omega naught equals 10, right? I can just go and program that easily in. Okay, and then run it. Okay, so the thing is the unit circle is here, but you can, because I didn't scale the unit circle by 10, because it wouldn't be a unit circle, but you can see the poles and zeros are still on a circle with 45 degrees. You can see that the Bodie plot now, the cutoff frequency has been pushed out, and that the step response, it takes longer to set to reach its final, it takes a shorter amount of time to reach its final value, right? Where if I put it back to 1, now you can see the original plot. Now here's the thing, we can do out of control systems as well. So what if I subtracted omega naught squared, right? We're going to have a pole on the right hand side, and we can see that. So there's the unit circle, but now we've got a real pole here on the left hand side and a real pole on the right hand side. Now the Bodie plot looks still low pass, but notice the magnitude does this strange thing. Also, this is in radians, not degrees, and I have to talk with the El Capi person to see if I can get that into degrees. But notice the step response. I'm getting exponential increase. Even the impulse response is doing that. All right. So I will post that code. It's a little rough right now. In this style business, there's a way to fix it. Again, I had just gotten off of chat with the inventor of this system. All right. So you should be able to link everything in a nice plotting format with systems that are in control, out of control. I forget what the okay, that should give me 2 complex poles. Okay, which does this odd thing, right? Which I'm not really familiar with this kind of Bodie plot, but usually when we have complex poles, we're not taking a Bodie plot of it. But you can see that here's the sine wave or cosine wave that's propagating. All right. So that took a chunk of the weekend to do. Now today we're talking about, oh, and just so you know, that new tool I was using, or new module, is L Cappy linear circuits applied Python. And the person's pretty responsive. These notes are here in the module. And I must say that my getting started with modulation notes, there's some parts that are good, and honestly, there's some parts that might be a bit confusing. And so I actually started on these notes a few weeks back to try to make sure that modulation would proceed smoothly. Okay. So anyway, modulation, it's pretty hard to overstate how important this is to modern day communication systems, right? Because if we couldn't put our data into channels, right, which aren't, I mean, they exist in the real universe, but they're not like a physical channel dug, you know, like the Suez Canal, right? So if we couldn't modulate information as we put it into the ether or various mediums, we'd all be kind of taking turns to talk, right? Now, what kind of various media are we talking about? Well, first one that springs to mind is we can send vibration data, right, down a string. We have these kids, and I never thought of doing it this way. I've only ever seen, one end to one end where one person holds a can and the other one holds a can and there's one string. But all these kids are all on the same communications channel, except this guy right here, because it's loose, right? So he's not going to hear anything. And so this is, really a great model of what will happen if we don't have modulation. While everybody can hear, right, only one person can transmit at a time, right? And again, since everybody can hear it, right, it's not really that secure. All right. Now, here's the thing, our air, right, we can have pressure, music, talking. And if you all remember what classrooms were like, right, back in the day when we had classrooms and we saw each other, in general, the professor spoke. And if somebody had a question, the professor would hopefully notice the student wanted a question, stop speaking, and then let the student ask their question. But really, you can only have one person at a time, right? Now, when you broke up into groups, everybody's talking at once, but the way we're kind of able to get away with that is if you're talking quietly in a small group, your voice doesn't really travel that far. And also your brain is actually filtering out the data you don't want and trying to concentrate on whoever you're really trying to listening to. So there might be no modulation, but there is some filtering going on, right? And again, even if you'd say, well, professor, put it in the electromagnetic spectrum. Okay, but without modulation, right, we're all kind of transmitting at the same data rate that we're speaking, right? So if my voice is between 20 and 20 kilohertz, right, and I'm broadcasting exactly my voice into the electromagnetic spectrum, it's taking up 20 to 20 kilohertz, right? Now, water, you have pressure, you can have E&M, or cable. I like Xfinity, right? That's electromagnetic, right? But think about it, you'd only be able to have one channel, right? Because you'd have one wire. Telephone wires right? I'm sure they work like that. And now even fiber optic cables, right? They're using light. And in fact, when they first had them, there only was one channel. And what you did is you just kind of broke the data up and you took turns. Okay. So when you're taking turns, another way to talk about that is, or to call it, is time division multiplexing. All right. So now, just so you know, that with cell phone data, not only are we modulating into channels, but we are also kind of taking our turn. It's just happening so fast that we can't tell. All right. Now, a common type of question that can pop up on an interview is like, how does a radio work? Right. And they're not necessarily looking for the answer that you'd be able to give if you took EE 160, but it's kind of like a general thing. All right. And I'm going to get into the mathematics of modulation in a bit. All right. But basically, you convert a pressure signal, right? Talking music into electrical, right? That's like a microphone, right? And then before you modulate it, you make sure that your data is in the right frequency. So there's some band pass filter with gain, right? Then this is really the key. You multiply that signal by the carrier frequency. Now, that's like the simple way to talk about it. There's amplitude modulation, frequency modulation, phase modulation. That is much more advanced than we're going to get into. We're just going to talk about this simple modulation. All right. And then you take that signal and push it out through an antenna, right? The antenna receives the signal, and the antenna is actually a filter as well, right? Is that you try to make sure that your antenna is the right length to be picking up the right frequency ranges, right? Now, here's the thing: if you are sending on one carrier frequency, right? If the two of us, if we have two people trying to transmit on the same carrier frequency, right, that's interference. And if you are running an illegal radio station on the same at the same frequency, what is 98.5? What is that? Megahertz? Anyway, 98.5, right? And you start broadcasting on that, the FCC is going to come down on you because you are interfering with that channel. That's why the radio, right, has all these channels and they're separated by half a unit, which is escaping me right at this moment. Anyway, so you use a bandpass to get the channel that you want, right? Then this is the really interesting part, is you multiply that bandpass signal by the original carrier signal, meaning, if you had a 1 megahertz signal, you'd have a 1 megahertz carrier. You'd have a 1 megahertz sine wave on your radio. All right. And when you do that, you actually get back the original signal plus that carrier wave, which then you have to get rid of, right? So you filter out what you don't want again, and which would be low pass in this example I'm giving. And then that electrical signal is converted back to pressure, right? Which is nice, big, cool speakers. All right. So I'm going to lead you through this still intuitively. All right. and with an LT spice simulation. All right. So this is my data. All right. And this is a chirp signal where, so it's a cosine 2 pi times 100 times time, but then I multiply it by time. So the period is changing as time goes on. And so you can see that signal get faster and faster. And the thing is if you were to listen to it, it sounds like a chirp. So this is called a chirp signal. Now C is the carrier wave. And it's at a frequency much higher than the data. And that's why it's, these simulations can take a long time and they use a lot of data, because that's 100 kilohertz sine wave simulated over 500 milliseconds, right? So if I just zoom in on that, you can see what's going on, right? Now then I modulate it, which is I just multiply these two together. And I'm going to start deleting things so that we can, okay. And this is the signal that's sent out, right? And then here we have a receiver, which is a bandpass filter, which I just did a behavioral, and I made it, I was trying to capture more of the bandwidth. So I didn't use a Butterworth. I set a damping coefficient of 5 to try to catch more data. All right, and these time domain signals do take a bit to plot. Okay. And it might look kind of just the same. All right. But you'll see that it has been changed. And then I take that band pass and I pass it through my demodulator, and you can see I'm just multiplying it by VC, and then I put it into a filter. And yeah, now you might see why now is the time to look at the FFT here. And you will see that it's a lot easier to look at. Okay, so let's look at the data first. All right, so here's the data. And that chirp signal, notice it's kind of flat and then it rolls off. So it's got a lot of frequency information in there, which is why I used it. And you can kind of see that there's a lot of information here, and that at 100 hertz, it just rolls off practically down to 0. Okay. The carrier, right? You can see one strong peak here. Now, these other, it can be somewhat hard to interpret the rest of this, but that's really like numerical noise. Because if I just put it on a linear scale, I can see one clear peak. Why isn't it 1? Because LT Spice puts everything into RMS. So if I convert it back from RMS, you can see there's my 1. All right. Then where is my modulated? Here's my modulated. Okay. Now, yeah, it does change the scale, right? but it looks like there's just one peak there, right? However, if I zoom in, you can see it's actually spread out and that the signal is symmetric about that. All right. So I take that signal. Oops. Get rid of that. Right. And now, so that's my modulated data. Now, if there were all these other radio stations around, like at 11, 12, so-and-so, or 2, 3, and 4, I would want a band pass around that. And that's what I tried to do. Although I might have. So now that band pass, right, it reduced it, but because that's kind of what the filter's doing, or I might be at the wrong. Anyway, that's the bandpass filter. Now oops. Now I multiply that back. And this is still here. And now I have to go to the decibel scale. Okay. This is still here, right? Even though it's been reduced in magnitude, that is very close to our original signal. It's just scaled down. This, yeah, that's a real signal, but we just are going to do a low pass filter of that. And which is that right there. Okay. And now this is what we would listen to, right? And yeah, there's a artifact here, but if this were a real radio signal, this would be so much higher that our low pass filter wouldn't pick it up at all, right? But there's kind of like, you know, our original data. Now, yeah, hey, Justin, I see your question, but is that about today or later?
It's about today. It's about the 60 hertz clock.
That sounds like last lecture.
It is.
Okay. Yeah, so I'm gonna you know, we can meet during office hours to go over that, okay? Or if I have time left, I can try to go over that, but I have to bring all that up, okay? So that's kind of what's, you know, really going on there. Now, mathematically, okay, remember, we multiplied the data by a carrier wave. Now, remember, any data, right, if I say that it's repeating forever, is made up of sines and cosines, or really just cosines with phase delays, right? So if I can show something for one cosine, then I can get the original back. All right. So, but here's the thing, without the Fourier transform, right? Let's just say, what if I use this transform, right? If I have two different, a sine wave at one frequency and a sine wave at another, and I just multiply it by 2, right? I can convert that into a cosine minus some frequency and a cosine plus a frequency, right? And this assumes that phi is less than theta. All right. So if I take a sine wave of one frequency and multiply it by a sine wave of a different frequency, right? If I take the Fourier expansion of that, I just get two separate cosines, right? At slightly different frequencies. All right. So that trig identity is somewhat at the heart of it. So if I take, if I'm singing a pure note at one frequency, and then I multiply it by a carrier frequency, I'm going to get a signal that one part is at that carrier frequency minus the frequency I was singing, and then another one it's going to be at the carrier frequency plus, right? And that's just a trig identity. But you kind of, to really see where that comes from, you need the Fourier transform, okay, which is here. What's the difference? Well, instead of S equaling j omega, instead of S equaling a real plus an imaginary part, things just equal j omega, and then the integration limits are negative infinity, positive infinity. That's why it exists, for all time, right? So let's just do the delta function, which is kind of just done by inspection, really. But here's my f of t, right? Something delayed by a. So I just put it in here, multiply it by e to the j omega. And here's the thing, right? If I'm integrating from negative infinity to positive infinity, right? What happens is this only exists at a, right? So this t becomes a, and then that becomes the 1 because you integrated over it. All right. So it's practically, just right. If you integrate a delta function, right, you're going to get 1. If you integrate a delta function times another function, you're going to get the value of that function at the time the delta function was active. All right. So, and so what happens is this makes it into a, so here's the thing, if that's true, then the reverse is true, where if I have something e to the JAT, then the Fourier transform is a delta function. And really, that's the easiest way to do it. Meaning a lot of times you find the transform and you just find as many functions as you can. And then that's how you know what the inverse was, right? So if I start with a delta function and get an exponential, well, then if I start with an exponential, even if it's in the time domain, well, then I'm going to get a delta function. All right. Okay. Now we go to cosine. All right. So what one does is you put it into the exponential form. All right. Then you put it into the Fourier transform, right? Which we have started with exponentials. So now we're going to get delta functions, right, that exist at your positive and your negative frequencies. All right. And so remember, I said the Bode plot is from this point upwards, right? But there's nothing, that's a Bode plot. The frequency response actually has a negative, it goes from negative to positive. All right. So if I made this a linear scale, then I could handle the 0 and I could go negative. All right. But Bodie plots just deal with positive. All right. So anyway, the sine wave can be found as well, except it's scaled by 1/2j. All right. Okay. So that's a lot to say that a cosine in the Fourier transform of a cosine are two delta functions, right? And at the frequency of the original cosine, positive and negative on the frequency axis. All right. Let's modulate this by a carrier wave. Let's do that. So if I have a signal, right, it's just cosine 2 pi 1 kt, right? And then I have a carrier signal that's 100 times that, right? The data becomes these two two delta functions, again, positive and negative frequency. The carrier signal becomes something with negative and positive frequency. And now here's the thing, multiplication in the time domain becomes convolution in the frequency domain. But in this case, so we have to convolve the data times the carrier, which normally you'd think, oh no, I want to use Laplace or something, right? But no, it's actually quite easy because we're just convolving delta functions, right? And whatever you convolve with a delta function is in fact the scaled and delayed version of whatever it was you convolved with it. So the final data here is, here's my original one. This is my data at a negative and positive frequency. And then here's my carrier at a negative and positive frequency. And so I just have to multiply through, like FOIL, each one of these. And it gets a bit hairy, right? But when I go through it and start, combining terms, right, I get minus 2 pi 101k plus 2 pi times 99k. And then you can see that I have the negative version and I have the positive version. So in fact, if I group these, I'm going to group these over here where I have the minus 99k and the plus 99k, the 101 plus and the negative 101. Okay, so I'm just going from here to rearrange it, and it's divided by 4. Well, then I can then take the inverse Fourier and convert it back into cosine, and that's 1/2, right? And that's 100k minus 1k, and that's 100k plus 1k, which was, if we go way back, right, that's practically this definition, okay? Right, that original trig identity. And remember that homework where, find the Fourier expansion of sine squared or cosine squared, and then find the Fourier expansion of sine cubed or cosine cubed, right? Where we could, do it with trig identities. But really, you need to know this because it tells you where it comes from, okay? So there we go, right? That's how we get the signal to be modulated at that higher frequency. All right. This is the link to that LT Spice file I showed. Actually, in the sample I uploaded, I didn't put in that bandpass. There was something I didn't quite like about it. So, but it shows, almost every step. And that bandpass would really be because there were all these other signals modulated. So to make a really good example, I should have like 10 carrier frequencies and 10 pieces of data to see if I can actually select one. All right. Where'd it go? So what I want you to think about with this is we can call that magnitude. It can be on a linear or dB scale. And that data, right, it has which is made up of cosines, right, or cosines with phase, right? Whenever you have a cosine in the frequency domain, right, you get a positive and a negative version of that. Okay, so this should be exactly symmetric. All right. In the book, he likes to do this. Well, I'm having trouble with symmetry. All right. So just call that, you know, the data. Right. And then over here, right, I have my carrier frequency. Minus FC plus FC, and that's 0. And to modulate, I convolve these. All right. So that turns into, and I'm going to put it right here. Right, where those are the original, that was the original carrier wave part. And then here, rather than be centered around 0, okay, and even so, this is X omega, right? But really, you know, the Fourier of xt equals x omega, and this is really over here sine 2 pi fct, right? And the Fourier of that equals our move this out of the way. Okay. Now, I'm sorry, I probably confused you a little bit because I'm using frequency and radians. And so it seems when we're talking about modulation, we actually use frequency, right? And 2 pi f equals omega. All right. So anyway, this signal is what gets sent in, right? So you could say y mod of t equals xt times cosine 2 pi fct. Okay, and this was, you could think of it as that chirp signal or somebody signaling or music, and that there's just this range of frequencies in there. All right. So here's the really interesting thing, right, is that now I want to demodulate it. Now, yeah, of course, if this is in the ether, I'm going to have to use a bandpass filter to capture this. to get rid of all the other radio stations, right? But this is going to be y mod dt times cosine 2 pi fc t. And you do, this is in your receiver, and you do have to adjust it to make sure that it's in phase with the original signal, but there's more than that. So now what do we get there? We get x of t times cosine 2 pi fct squared, right? And I'm just gonna, well, that means we get x of t. And what was that? What was the trig identity of that? 1/2 plus 1/2 cosine 2 pi 2 times fct. Now, while this is a DC component, this is a time varying signal, right? And you get back okay, so I get, and this isn't drawn to scale, just so you know, right? This is xt times 1/2, and then I get okay, this, all right, and this, the axis is frequency, the units are hertz. So this is our original data. Now, yeah, it's scaled by 1/2, but we can always use an op amp with gain, right, to bring that up, right? And so this is our original data. How do we get that original data back? Well, we use a low pass filter, which this is what a low pass filter looks like on a linear scale on the X and a linear scale on the Y. All right. A Bodie plot, right, would have a log type thing, and it would look like that. This is what it really looks like when everything is linear. So you just draw a box around it, and then there you go. There's your original signal. All right. Now, I have examples where rather than do this, right, I actually, you know, here's a sine wave that's data. Here's a carrier frequency. I convolve them and then multiply it again. But what I've found is just thinking about it like this. Don't worry what xt is. It's just some signal of the bandwidth. And that's really all that's going on, right? And that's all you have to say on the homework. Okay.
Professor,
Yes.
I want to verify whether or not I'm understanding this correctly conceptually. Okay, so basically, the point of modulation is the basis that when we combine different signals together, it's basically impossible to understand the message. So the point of modulation is basically so that we make it so that we can essentially discriminate between the signals we do and don't want. And the way we do that is that we take a signal, we modify it in a very certain way, and then once conditions are met, we basically demodify it, and then we just make a couple adjustments to get the original signal back, right?
That's pretty close. What I would like to add is knowing which filter to use and when, right? Use a band pass when you get the signal from the antenna. Use a low pass after you've done that. But as a high level, yeah. And of course, just because you've put a frequency at 1 megahertz Doesn't mean somebody else can't do that. And that's what jamming, right? As part of all science fiction movies when you're jamming a signal. Right. But
Okay, but it seems like I got the general idea behind it,
you
right?
did. And I just, as a professor, I've always got to somehow criticize things. Okay. So I was just kind of giving you a little more feedback. Now there was, there's an equation I want to use for another homework assignment that I just have to look it up. But did that answer your question?
Yeah, I just want to make sure I'm getting this right. That's all.
I think you're definitely headed in the right direction.
I have a question as well.
Shoot.
For our final, how will you be asking us for this lesson? Will you just be giving us two equations, one of them being the carrier frequency and the other being and what's the first signal
I mean, what is a typical exam problem
Yeah,
for
what's a typical-
modulation?
question for modulation? Yeah.
All right. Now I still want you to listen to me after I say the next sentence. All right. But a pure modulation question like this isn't really going to be on the exam. It's coming too late. But you need to know it for the following on courses, so you need to be exposed. However, things like cosine squared and all the other Fourier examples, or it might be, I'm giving you a slice of the radio and I'm asking you to explain something. But question 10, final exam, explain how a radio works. No, that is not going to happen. I'm just trying to prepare you for interview questions and just give you another application. Does that help?
Yeah, that answered my question. Thank you.
Okay. Okay. So I just want to hold off with questions just a smidgen. All right. Is that I want to revisit pulse width modulation a little bit. Okay. So all of these square waves all have the same period and they're all repeating. Okay. So the book uses tau yet again for how long you're on. But we can certainly just call that T on. All right. So that there is an equation for that, for the Fourier expansion. And I'm just have to and A is the amplitude. Okay. So this is A naught. And then what they've done is put it in a more compact way. All right. So we have 2A and I'm sorry, this is just tau, the period time, the period. So this is 2A divided by n pi. Okay. Sine n pi t on t cosine n, oh, sorry, 2n pi t on divided by t. All right. So let's just do a quick, so 50%, this is going to reduce to that pattern we normally know. All right. But here's the thing, as I change this value, notice this ratio is changing, and that's actually the data I want. And if I were to just draw, what would I want? I will draw a low pass filter over the term that I want, right? And this high frequency part is what I don't want. Now, I have a question is, can you use this to modulate a signal, right? So I can take a signal and make this dependent on, whatever the amplitude of my voice is, how long it stays on changes. Okay. So let's take the first term, right? Let's use a darker color. N equals 1. All right. So we have 2a divided by pi. So that stays the same, right? So there's no way to modulate it just yet, right? Because that's just a constant. But if I have sine pi t naught over t cosine 2 pi t naught over t, I'm just going to scroll down a smidgen. And here's the thing, this ratio, t naught over t, in a real system, right? This is changing with time. That's how I'm encoding the data in a pulse width modulated DAC, right? I'm not really just making a DC filter. I mean, a DC power supply, right? This is in fact changing with time. And so since this is changing with time, this value of sine and cosine are changing. And so this value of the first harmonic, right, would be going up and down in time. And if I wanted a different harmonic, all right, let's say that first harmonic was at 100 kilohertz, right? But I needed 500 kilohertz, but I only have a 500 kilohertz PWM. Well, that would be 500 500, 1 meg, 1.5, and so on as you multiplied it out, right? Now, why is that F2 there? Well, I'm just saying it's not exact, it's not 50% duty cycle. This sometimes disappears to 0, as you know, right? For 50%. But if you keep the ratio at a certain value, right, and don't let it go from 0 to 1, right, you can modulate whatever peak you want. All right. And that's just a kind of a hint to get you in the right thing. Now, if this whole thing goes into a low pass filter, right, what should that look like? Well, I'm just going to call that, this is A, B, and that's C. So this is repeating. So if the filter starts out at 0, right, it's going to be kind of doing this and go up here, and it should ultimately end up at a divided by 2, right? That's a. Now this one, I'm trying to show the ripple there. That would be a divided by 3/4, right? If that's on 3/4 of the time, right? And if I were to do the half, okay, I would have a divided by that. All right. So that's kind of what's happening, except you're not always going back to 0. You might be at a half and then go to 3/4, or then you might go down to a 10th, or whatever the number of bits are. All right. But so what I'm trying to show here is, rather than here's the signal, right? But I want to draw that 10 cycles of each one of these, which will be kind of hard to draw, right? So I'm saying, rather than drawing 10 cycles, I'm saying 10 of a 50% duty cycle wave, 10 cycles of a 10%, 10 cycles of a 75%, and then I'm going to put that into a low pass, right? And what I should see, is something like this: is I start off at 0, right? Oops. And it'll take some time, right? Then in time, it changes to 10%. So it goes down. Then I guess I should go back to blue. Now there is ripple in here because the filter isn't perfect, right? But that would be 75%, 50%, and 10%. All right. And so I'm trying to say is that these things change over time and effectively become DC. Okay. But that's what you would see. And then if so, I'm just going to say, if I started with 1/8, 2, 3, 4, 5, 6, 7, and 8 out of 8, which you wouldn't really see. So I'm just saying, what if these were just blocks of time? In those blocks of time, that's the duty cycle, right? What would it look like? Right? It would go up, and then up, and then up, and oops, and then up, oop. Okay. Which, you'll kind of always have and here is in fact, every time it changes values like that, that's actually a mini step response in there. Okay. And that time it takes to settle is related to the order of your filter, right? The higher the order, the longer it takes, right? And what your cutoff frequency was. All right. Hopefully you can understand pulse width modulated DACs a little bit better. All right. Well, this was an in-class activity that we actually already did. So, which you can go and do on your own rather than in class. I wanted to. Yeah, so what I'd like to do is actually, in the remaining time, do module 27's in-class activity. All right, and it's and see how that works. Now, just so you know, on the final exam, it'll deliver the question, but you don't answer it in my open math.